In today's design session, we are going to talk about system design for Search Autocomplete System. It's an interesting system. So what is Search Autocomplete System? When searching on Google or shopping at Amazon, as you type in the search box, one or more matches for the search terms are presented to you. This feature is referred to as autocomplete, type ahead, search as you type, or incremental search. So in the figure, you can see it represents an example of Google search showing an autocomplete results for when dinner is typed into the search box. Now, Search Autocomplete is an important feature for many products, and which leads to the interview question: design a Search Autocomplete system, also called design top K or design top K most search queries. So before we go any further, let's remind ourselves of the design discussion framework. As part of the discussion, we should first establish the problem statement. We should align on requirements, do some back of the envelope calculation, which might involve some napkin maths, agree on tenets and variants for the solution, then discuss system correctness or operational requirements, and also outline the in and out of the scope things. Then as part of the kind of actual design, we should first start with the high level design, then go deeper into low level designs, and depending on kind of interviewer interests or time, we can go into, we can dive deeper into specific topics. Then we could discuss failure modes and also discuss operational readiness requirements, which could be metrics, experiments, security reviews, and durability aspects of the design. So let's establish the design scope for this particular problem. So first, it's an auto suggestion at the end of the search query. Let's say it's 3 to 5 auto suggestions. The suggestions are determined by popularity. English is the language supported, no spell check, no capitalization support, and let's say it's around 100 million DAU. To summarize the requirements, first we need a fast response time. As a user types a search query, autocomplete suggestions must show up as a fast enough. An article about Facebook's autocomplete system reveals that the system needs to return results within 100 milliseconds, which is actually true. So anywhere between 20 to 100 milliseconds is fair. Now, relevancy. Autocomplete suggestions should be relevant to the search item, which is kind of obvious. Sorted. The results returned by the system must be sorted by popularity or other ranking models. Scalable. The system can handle, high traffic volume. Highly available. The system should remain available and accessible when parts of the system is offline. It slows down or experience unexpected network errors. So let's do some napkin maths. So let's assume 100 million daily active users, and an average person is, let's say, it does 10 searches per day. Assume 20 bytes of data per query string, and for every character entered into the search box, the client sends a request to the backend for autocomplete suggestions, and this amounts to around 240k queries per second. And if we take peak QPS as double of that leads to 480k or like around 500k QPS. And in terms of storage, it might mean 4 GB of new data is added to the daily storage. And you can see the maths in this slide. So at a high level, the system is broken into two major components. First is data gathering service. It gathers user input queries and aggregates them in real time. The second is query service. Given a search query or prefix, return 5 most frequently searched items. Now, talking about data gathering service, it gathers user input queries and aggregates them in real time. Query service, given a search query or prefix, it returns 5 most frequently searched items. Assume we have a frequency table as shown on the right hand side, and it has 2 fields, query and frequency. So query stores the query string and frequency stores the number of times the query has been searched. When a user types, let's say TW in the search box, the following top 5 search queries are displayed, assuming the frequency table is based on the table. Like TW, it could be Twitter, Twitch, Twilight, Twin Peak, Twitch Prime. We'll dive into a few components and explore optimization as follows. First, we'll look at the try data structure, then data gathering service, query service, scaling the storage system, and try operations. Now, I'm assuming that you are familiar with the try data structure. If not, search it up and get a basic understanding. So, for example, here, the diagram shows a try with search queries like tree, try, true, toy, wish, win. And search queries are highlighted with thicker borders. So you have a root, and then you have the tree, and on the leaves you can see tree, true, try, toy, wish, win. After adding frequency info to the nodes, updated try data structure is shown in the figure. So for example, tree is accessed by 10, true 35, try 29, toy 14, wish 25, win 50. How does autocomplete work with try? Before diving into the algorithm, let us define some term. P, which is the length of a prefix, and total number of nodes in a try. C, number of children of a given node. Now, steps to get top K most search queries are listed below. For example, first, find the prefix for which the time complexity will be order of P. Traverse the subtree from the prefix node to get all the valid children. A children is valid if it can form a valid query string, for which the time complexity might be order of C, and then sort the children and get the top K, for which the time complexity might be C log C. So net the time complexity is the summation of order of P plus order of C plus order of C log C. The above algorithm is straightforward. However, it is too slow because we need to traverse the entire try to get the top K results in the worst case scenario. And below are two optimizations. First, we could limit the max length of the prefix, and second, we could cache the top search queries at each node. So limiting the max length of a prefix. Users rarely type a long search query into the search box. So it is safe to say P is a smaller integer, say 50. If we limit the length of a prefix, the time complexity for find the prefix can be reduced from order of P to some constant. Then we could cache top search queries at each node. To avoid traversing the whole try, we store the top K5 frequencies queries at each node. Since 5 to 10 autocomplete suggestions are enough for users, K is relatively small number, so in our specific case, only the top 5 search queries are cached. So here the figure shows the updated try data structure. The top 5 queries are stored on each node. For example, the node with prefix B stores the following: best with frequency 35, pet with frequency 29, B with frequency 20, B with 1E with frequency 15, and bear with frequency 10. Now let us revisit the time complexity of the algorithm after applying these two optimizations. So finding the prefix node, the time complexity is constant. Returning top K again is constant because it's cached. So our total time kind of reduces to order of P. Here we'll talk about data gathering service. So as we can see in the figure, we have analytic logs, then we have aggregations, we have aggregated data, then workers, which update at some frequency. Let's say it's weekly here, which is not very realistic, but let's assume for the time being. So it updates the try DB, and then there's a weekly snapshot which gets cached into the try cache. Now aggregators, the size of the analytics logs is usually very large and data is not in the right format. We need to aggregate data so it can be easily processed by our system. The workers. Workers has a set of servers that performs asynchronous jobs at regular intervals. They build the try data structure and store it in TryDB. Now try cache. The cache is a distributed cache that keeps try in the memory for fast reads, and it takes a weekly snapshot of the database. As I said, the weekly is just some random frequency. In any practical or real life situation, it won't be weekly. It'll be some frequency, not weekly. Then try database. The try database is a persistent storage. Two options are available to store the data. It could be document store, or it could be key value store. Now generally it's key value store, because the try can be represented in a hash table format by applying the following logic. Every prefix in the try is mapped to a key in the hash table, and every data on each node is mapped to a value in the hash table. And this is the diagram for try hash data structure. So you have the try on the left hand side from the root. If you go to B, B will be the letter B will be the key, and the hash value is the set of words or suffixes which are stored at that particular node. So in this case, it is B with single E, then B with double E, and beer and best. For the query service, the flow looks like as follows. The search query is sent to the load balancers. The load balancer routes the request to API servers, which is pretty typical. API servers get try data structure from try cache and construct an autocomplete suggestion for the client. In case the data is not in try cache, we replenish data back to the cache. This way, all subsequent requests for the same prefix are returned from the cache. Cache miss can happen when a cache server is out of the memory or offline. Try is a core component of the autocomplete system. Now let's look at how try operations create, delete, update work. Create. Try is created by workers using aggregated data. The source of data is for analytics log or DB. It could also be through some streaming services. Update. The update individual try node directly. We try to avoid this operation because it is slow. However, if the size of try is small, it is an acceptable solution. When we update a try node, its ancestor all the way up to the root must be updated because ancestors store top queries for the children. Now update. Updating individual try node directly. We try to avoid this operation because it's slow. However, if the size of the try is small, it's an acceptable solution. When we update a try node, its ancestors all the way up to root must be updated because again, ancestors store top queries for children. Delete. We have to remove hateful, violent, or sexually explicit or dangerous autocomplete suggestion. So we could add a filter layer in front of the try cache to filter out unwanted suggestions. Having a filter layer gives us flexibility of removing results based on different filter values. So now scaling the storage. If we analyze the historical data distribution pattern and apply smarter sharding logic as shown in the figure, the shard map manager maintains a lookup database for identifying where rows should be stored. For example, if there are similar number of historical queries for S or for U, V, W, X, Y, and Z combined, we can maintain two shards, one for S and one for U to Z. So here are some final thoughts. So the follow-up question could be, how can we support the real-time search queries? Now, supporting real-time queries is a bit complex. The design proposed here, or the way in which it was discussed so far, it won't work because offline workers are not scheduled to update the try because they're scheduled to run on some predefined frequency. Even if it is scheduled, it'll take too long to build the try. Building a real-time search autocomplete is complicated, but here are some ideas. You could reduce the working data set by sharding. You can change the ranking model and assign more weights to the recent search queries, and data may be coming as streams. We do not have access to all the data at once in that case, and streaming data means the data is generated continuously. So we need to update the try at some near real-time frequency. Here are some good reference materials for you to follow up on the discussion so far. I'll highly recommend reading The Life of a Type-Ahead Query and How We Built Prefixy. And then, if time permits, you can go through the rest of the references as well. That's all I got. Hope this was useful. Have a nice time. Like, subscribe, and comment for more such designs.